So welcome to today's webinar. It's a great pleasure to introduce Lee Ma from Duke University. Lee's worked a lot on trees in particular, but also some applied problems in bioinformatics. So I'm just going to hand over to Lee, and he can tell us all about his 2000 trees.
Thank you, Jim, for the introduction. Thanks for to the organizers for inviting me, and thanks to everybody for your presence. So I'll see if I can get to the 2000 part. I have to go through the two-tree part. So everything I'm going to present today is going to be from joint work with my former student Naoki Awaya on the left, and also my current postdoc Akira Horiguchi. And I think they're both here. Instead of if you want to show your face or not, it's up to you. And also I'd like to acknowledge the funding agencies for making these research possible. So what is the two trees? I'm going to start my talk with. In the general BNP literature, there are two very well-known type of models. The first type is the so-called tail-free process, and one of the most famous example is the so-called Polya tree, which was first introduced by Ferguson, but really made popular by some later papers in the 1990s. And these models are generally as alternative for modeling random measures where a density is needed. And in the last 10 or 15 years, a lot of the literature in the BNP community utilizing these processes are for hypothesis testing and some model choice problems, because under common specifications of these models, the marginal likelihood is available analytically, so it makes applying these models very easy. Another type of process I'm going to talk about is often used in mixture modeling, discrete random mixtures, and they're called state-breaking processes. People are also in this community very familiar with these, although it's not very frequently associated with trees. But I will show in my talk that these two types of models are really sharing a lot of structures. And in particular, among the various tools for mixture models, state breaking is often used when there's a need for incorporating covariate effects, because of the fact that by constructing the generative model of mixture weights using state breaks, you can very easily incorporate dependence on covariates by modeling the binary problem of breaking a stick under the traditional McKeegan framework for a dependent mixture model, dependent and discrete random measures. So I'll just give you a quick review. The most famous tail-free process, the Polya tree, basically it is a tree representation for any arbitrary distribution. You can give me any distribution. I can construct this recursive partition, dyadic partition of the sample space, and specify this distribution using the left and right splitting probability that characterizes how much relative probability mass that goes to the left versus the right. Here I'm using theta of A to indicate the proportion of mass going to the left on the set A. And you keep going, specifying more and more details as you go deeper. Eventually, you're gonna characterize the whole distribution. The Polya tree model, which could be used either as a prior or in multi-sample problems as a sampling model, is simply the most simple conjugate model for these branching probabilities, which is just the independent beta models. We can show that the likelihood under IID experiment from Q, if there's a density, can be factorized into the product of binomial split likelihood, and therefore the conjugate prior is the beta prior. The posterior has a closed form beta update. In the multivariate case, the traditional way of building Polya tree is to split the space symmetrically in both dimensions. Let's say if you have two-dimensional space, which will give you a quad tree, and if you have 3 dimensions, it will be A children. and replacing the beta prior with Dirichlet priors. And this model is actually also studied almost at the same time in the 1990s in the frequentist literature under the name Dirichlet tree model. So the state breaking process generally was formally introduced by Ishwar and James, although it was used in various forms earlier, is basically a generative model for a set of weights that sum up to 1. And it's a generative model constructed by sequentially breaking up a unit stick and putting various different priors on these stick breaks, right? So the form that's introduced by Ishwar and James is basically also this independent beta priors. There are also famous processes such as the for Dirichlet process, and later in the covariate dependent setting, David Dunson, my colleague and co-authors, introduced probabilistic state breaking, logistic state breaking, and so on and so forth, corresponding to different priors for these V's. Now, the interesting part is that if you view the state breaking from a tree perspective, it is also a tree, although it's not a symmetric tree. It's a tree that sequentially divides up the unit interval essentially under the Ishwar and James setup with independent beta priors. So it's essentially the same model as Polya tree. And indeed, if you apply this model in mixture modeling and use a block Gibbs sampler to update these weights, you're going to be exactly updating from the Polya tree posterior, where your data points are going to be the current custard labels within that iteration. So it's essentially embedding a Polya tree within the mixture model. There's 2 threads of research in each of the corresponding literature that utilizes the fact that you have a binary dyadic representation of probability mass that sum up to 1, so that you can incorporate covariate easily. So in the state breaking literature, again, as I mentioned, David Dunson and colleagues worked out probabilistic state breaking and logistic state breaking. And in the Polya tree literature, this paper by Hara and Hansen, 2010, is really really introduces this idea in the context of Polya trees or tail-free processes in general. And it's very convenient in that these strategies are very convenient in that once you take this dyadic representation, this decomposition, the inference on these covariate effects become basically the problem of inferring the coefficients of a binary regression. And therefore, there are a lot of computational techniques for binary regressions that could be utilized very easily. In those earlier papers, as we know that the famous Polya gamma augmentation was introduced in 2013. Those earlier papers did not use that technique, but the well-known latent Gaussian augmentation was used. And also, after 2013, all of a sudden, the logit state breaking logit link function becomes very convenient for introducing covariate effect on binary regression. And I recommend this recent paper by Durante and Regan, 2021, which very nicely described the various different computational techniques, including MCMC and EM and variational inference that utilizes the Polya gamma augmentation to do inference in the context of state breaking, but you can easily see that everything is applicable to covariate dependent tail-free processes as well. Another direction that I personally worked quite a bit on in the tree modeling literature, as I mentioned earlier, is their applications in the context of model choice and hypothesis testing. And in particular, one of the techniques that I've worked quite a bit on in the last 10 years is that instead of, as we remember earlier, for example, in the Polya tree, you have independent branching probabilities modeled as, say, independent beta or some other prior. You can introduce some latent state variables that incorporate dependencies across those nodes. So the easiest model would be some kind of a Markov model over the tree and in this plot, the different colors could indicate different latent states for the Markov structure, so that you can actually borrow information across the nodes to enhance your inference. Right. The idea of hypothesis testing is pretty old, using Polya tree or tree-based models is pretty old. For example, in those classical papers by Jim Berger and Sandra, and also this classic papers by Chris Holmes and co-authors. Basically, in those contexts, before introducing the latent states, the hypotheses are tested by assuming that there is a shared latent state, null or alternative, over the entire tree space. All the nodes share the same latent state. And my recent work mostly generalizes that to basically allowing different latent states at different tree nodes and building dependencies across them. Later I realized that, more recently I realized that this kind of idea of introducing latent states is also present in the state breaking process literature. If you look at Chen and Dunson 2009, they incorporated variable selection into the mixture weights under the probit state breaking setting, which is essentially also another form of doing hypothesis testing and model choice on the tree structure. Now, these are the backgrounds, and the focus of my talk today, though, is kind of complementary to whatever the existing development I've reviewed. I'm going to focus on the tree, because all these model techniques that I talked about and the computational techniques I talked about are all given the tree. So something that is of interest to me is what is the impact of the tree on the resulting inference? And can we do better inference in those settings by incorporating perhaps a better tree or collection of trees even, which is the 2000 part, right? And I will also, and very importantly, there are lessons from supervised learning that we can learn in which, for example, tree ensembles have been very successful. We know BART, we know boosting, those are all very, and random forest, those are all very powerful supervised algorithms using a collection or ensemble of trees. And can we do the same in the context of unsupervised trees? So those are the objectives I'm trying to hit here. So I'm going to focus on the two-tree part. I'm going to dive a little deeper into the role of the tree in the context of state breaking processes and the Polya tree and tail-free processes a little deeper. So first of all, we know that in the classical state breaking, because of this, I would say, lopsided, one-sided state break, in a sense that you always break your stick on one of your hand, right? So, and you don't break the stick on the other hand. The corresponding tree structure is a lopsided structure. So you keep breaking up, keep dividing the unit interval, but only extend the tree in one direction. Now, one well-known consequence is that it's going to introduce stochastic ordering of the weights, right? Which is a direct consequence of this tree topology. And also, because state breaking process is so useful for covariate modeling, and one natural question is, what's the implication for covariate models, right? So if we think about the state breaking process, if, for example, this node 9 corresponds to a fairly small cluster in your data, then in order to characterize the covariate effect on this cluster 9, you are actually, think about it, the covariate will influence weight 9 through all the string of upstream splits. So it's not a very efficient way of characterizing a sparse effect on a cluster, especially for smaller ones, which by stochastic ordering is kind of pushed to deeper levels of the tree. And in fact, you use numerous numbers of covariate effects to characterize the impact on relatively small clusters. Clearly, that's not very efficient. And we'll see in a couple of slides a phenomenon which is first noted by Abel and David in their probit state breaking paper earlier, which is that in covariate modeling, if you adopt this kind of state breaking mechanism, a lopsided tree structure, you tend to induce very strong prior cross covariate correlation in the random measures that you generate. We'll see. We'll see the phenomenon. I'll come back to it in a couple of slides. But let's look at the alternative. let's just replace that lopsided tree structure with a balanced tree structure, like what people do in tail-free process, which means that in breaking the stick, instead of just breaking it always on one hand, you break them symmetrically on both hands. And now, again, after a certain number of breaks, you maybe come down to a maximum level, which corresponds to the mixture weights, if you're using that as a generative model for weights in cluster models, in mixture models, right? Now, immediately we see that by symmetry, this balanced tree topology removes the stochastic ordering, right? And now every covariate effect, regardless of the size of the cluster, will be evenly represented by a moderate number of coefficients. So for example, if you have this 3-level tree, it will be corresponding to those few coefficients that is this 4-level or 3-level, depending on how you define the node level. But we can see that for a lot of clusters, you're going to be using fewer parameters to characterize the covariate effect. And we'll see that the tail freeness, if you specify the step break random variables independently across the levels, then that will also remove the cross-covariate prior correlation that was noted earlier by Abel and David in their paper. So one thing that I want to mention here is that by generalizing the tree topology to an alternative to the original lopsided tree, we introduce absolutely no complication in the computational techniques. Because remember, at the end of the day, the step that involves this tree topology within, let's say, your Gibbs sampler is the Polya tree posterior. And the Polya tree posterior doesn't depend on the given tree topology. It's just and in fact, if you don't use the Polya tree, even if you use logit normal as like the that's introduced in Howard and Hansen 2010, the tree topology, the computational techniques absolutely makes no use of the tree topology, and therefore the computational complexity and the techniques are identical under this alternative tree structure as under the standard one-sided step breaks. Right, so this is just a simulation to illustrate some of the phenomena. So the left-hand side is so the first row corresponds to a classical one-sided tree step breaks, and the second row corresponds to a balanced two-handed step breaks. And we can see that if we either order the if we don't order the weights, then we don't have any stochastic ordering for the balanced tree, but there's strong stochastic ordering of the lopsided tree. And also we see that if we order also the weights from the balanced tree so that we can make the two more comparable, we realize that the balanced tree topology also allows you to have more spread out weights for the same level of variance in the step break random variables, right? So the weights are much more extended out than the very sparse structure that we have for the step breaking, standard step breaking, right? So I come back to the previous phenomenon that I mentioned, the cross-covariate correlation. This was first noted by Abel and David in their 2011 paper, which is I think in the Bayesian analysis. They noted that if you do step breaking and use a introduce a covariate effect by under the Polya step breaking setting, then the cross-covariate, if you look at the prior correlation of the random measures that are generated across different covariate levels, then regardless of how you specify your prior on the covariate effects, they tend to have some pretty strong prior correlation. In this simulation example in our paper, we show that under very, very standard common setting, there's a lower bound of cross-covariate correlation of 1/3, regardless of, and we proved it, and analytically, you can prove that the lower bound is about 1/3. And whereas once you replace the tree topology, that lower bound is removed with a relatively small number of levels in the tree. Right. So that's about what I want to talk about under the sibling setting. Now let's move on to the setting of tail-free processes or Polya trees, where the goal is not to build a generative model for mixture models, but build a generative model for densities. Right. This example, I forgot to put the source. This is taken from my paper in 2017 on the adaptive Polya tree. So what I'm showing here is that if you look at the left plot, the red dashed line is the true density. And now I simulated, I think 100 data point, I forgot exactly the sample size. And I fitted a standard Polya tree model to it. With the k-square pseudo count as where k is the level of the tree. If you don't know what I'm talking about, that's okay. It's not key. And what I'm plotting as the gray line is the posterior mean of that model as the base estimate for the underlying true density. Now it's hard to see those two modes, so I zoomed in into those two modes, and you can see that there are some issues with the posterior mean, right? So first of all, if we talk about that from the perspective of frequentist performance and the repeated experiments, then we saw that there seems to be some over smoothing and shrinkage in this very spiky portion of the density. In the frequentist language, it will correspond to a high bias introduced by over smoothing or excessive shrinkage toward prior mean, right? But on the other hand, if we look at this left mode, and also in fact here, if we look at very high resolution, look at the details of these densities, there seems to be some under smoothing going on, that insufficient smoothing is causing some high variance due to not smoothing enough in those very tiny local details. But if you look even more closely, you realize that there's something going on more than that. Like in these sharp boundaries, which corresponds to where the tree splits the space exactly, there tend to be some artificial jumps and gaps that goes up and down, which is actually a type of bias caused by the restriction of the predetermined fixed partition tree. If you think about it, in this case, the partition grid is always the middle point or some fixed, the fixed quantiles of the fixed median of some distribution. Here is just the middle point. Because of that, there's some bias that's introduced due to the lack of flexibility of the underlying tree. Now, the latent state Markov modeling that I talked about earlier is really focusing on doing better shrinkage or other inference given the tree. It really does not touch on this type of issues. So really, in order to address this type of issues, we really have to think about how we can relax our constraints on the tree structure. Okay. So this is one example. So if I use I think the most advanced machinery, which was described in my 2017 paper called the adaptive Polya tree, in which case I put some latent state that follows a Markov structure. So you can imagine that the latent states corresponds to the smoothness of the function underlying density. And the latent state, the Markov model allows us to identify the appropriate smoothness in different parts of the sample space. Then you can really get rid of the undersmoothing and oversmoothing in the low and high resolution levels by introducing this model. But if you look closely, the jumps along those partition lines still remain. And it's just a different issue. If you're gonna deal with that, you have to remove the over-regularization or the constraints that you introduced by using a very restrictive partition tree. Now, I'm not the first one to note the issue of bias introduced by having fixed partition points. So in these earlier papers by Paddock and colleagues, and also these earlier papers by Hansen and Johnson, the idea is to introduce some hyperprior on those partition points so that you can average out, smooth out the jumpy nature along the partition points. So they are really hitting at the same issue I'm talking about, which is that you have to relax the partition grid construction. And in this other paper by Lewis and Peter, the strategy is different. They did not touch the partition grid, but they tried to model some dependency horizontally within the level. The hope is to kind of even out those edges without touching the partition grid. So this is a different strategy. I think I will consider it as some kind of a bias correction. Since you know there's this bias and you have some ideas of what the bias look like, you correct that bias. Whereas these two strategies these two earlier works are really hitting the issue of the restrictiveness of the partition tree and try to relax that. Now, none of these previous works are really scalable beyond one or two dimensions because of the fact that they utilize pretty sophisticated MCMC algorithms, and in my later talk, I try to resolve that issue with a solution that can really scale up to hundreds of dimensions. So, and there's another issue of the existing strategies for tree-based random measures, other than the strictness of the partition points, which is the lack of scalability in multidimensional settings, right? So if we just think about it, the traditional way of splitting up the sample space, if we adopt a symmetric partition scheme, then if we're in a k-dimensional space, then each time you split a node, you're going to have 2 to the k children. And if you go down the tree levels, the number of nodes in each level L is going to be 2 to the KL. It grows exponentially both in the level of the tree and in the dimension. So quickly, you're going to have, there's 2 issues that comes up. One is that computationally, you're going to have to deal with a lot of blocks. and if you want to work with a reasonably deep tree, like 10 levels down, it's very difficult to go beyond 3 dimensions because it's 2 to the 30th and more, right? But more than that, even if you have an infinite computer that allows you to do all these, suppose computation is not an issue, then there's another statistical issue, which is that the data becomes sparse very quickly as you go down the level, right? And because you're splitting your sample space into so many different blocks, and very quickly the blocks are going to contain no data. And depending on how you specified your model a priori, that could either result in high variance due to overfitting to very sparsely populated data blocks, or very high bias if you've imposed very strong smoothing assumptions a priori. Either way, the resulting inference is going to be terrible, right? So in graduate school, I worked with my advisor, Wing Wang, which resulted in kind of a partial solution, not total solution, but partial solution to the problem of data attrition. It does not fully address the scalability, computational scalability, but it was aimed at, aim at mitigating the data attrition problem. The idea is that, well, at least in most multidimensional problems, usually the underlying distribution is not symmetric in all directions. So you probably don't need to split them at up to equal resolution level at different dimensions. So why don't we incorporate a prior on the directionality of the splitting? Instead of splitting, let's say, a 2-dimensional block into 4, let's choose a direction to cut and then always do a dyadic cut into 2. So the idea is that then we'll be introducing some adaptivity into the splitting. Every time you split each level, you're only cutting your block into half rather than 4 pieces or 8 pieces and so on and so forth. And very interesting phenomenon that I realized a couple of years after this work, maybe in 2013, I realized that if you implement this strategy carefully, the computational complexity is exactly the same as the vanilla Polya tree with non-adaptive partitioning. That's actually shocking, pretty surprising to me when I first realized that. And it's very much related to the constraint that in this 2010 paper, we require that the cutting point, even though we can adaptively choose the cutting direction, the cutting point still has to be predetermined. Let's say the middle point. 2 or 3 years later, I realized that because of that predetermined cutting point constraint, it turns out that the computational complexity is proportional to the number of all possible nodes, not the number of all possible trees, which is massive because many different trees share common nodes. So the computation is actually, you can show that it's actually the same complexity as the vanilla Polya tree that does not have adaptive partitioning. And then the problem is that, well, if you don't have if you want to even relax the constraint that you have to always cut at predetermined points, then the computation is, again, not tractable. Right. I just show you one example fitting this so-called optional Polya tree from the 2010 paper, where we have 2 data modes, which in this portion, the data is only, having density gradient in the y direction. And this is a Gaussian node, Gaussian kind of mode. And I plot the posterior mode of the partition tree. Although we have the full posterior, you can show that it will, you'll see that it will adaptively choose to concentrate posterior mass on divisions that kind of characterizes how the density is changing, rather than dividing always symmetrically. So this is a partial solution. It's partial for 2 reasons. One is that it did not touch upon the predetermined partition point problem, and therefore the bias that's due to the strictness that you always have to divide in the middle of some other, the median of some other distribution still remains, and it doesn't resolve that. And also, it's still, the computation still grows exponentially in dimension and tree depths, and you generally cannot apply this model to data beyond 5 to 10 dimensions. So, so now just a quick summary, and we'll get, and I'll get into some new methodology here. So, so there's bias variance trade-off, and the previous modeling strategies very effectively addresses the bias variance trade-off due to shrinkage. But it did not touch upon the bias that's introduced by overly restrictive partition points. So then the natural question is, in supervised problems, we know that people have been using like very general tree priors like Bayesian cart, which does not put any constraint on where you can divide the block. Then why don't we do that here? Now we know that once we do that, the computation is going to be difficult because we're already not able to scale the unsupervised trees to high dimensions. What's the hope if we even allow the partition point to be more flexible? Right. So this is what we're going to try to accomplish. Right. We're going to try to adopt very general priors on the partition tree, and then design a computational strategy that can scale, which I will talk about in detail. And then the next question is, well, we know that in supervised problems, single tree models are much worse predictive models than in terms of predictive performance than tree ensembles. And if we're able to build very flexible tree base learners for the unsupervised problem, how do we actually, can we do something similar as in supervised problems by building ensembles so that we can have ensemble models that can characterize high dimensional probability distributions that who can blow away the performance of single tree models. Now, the prerequisite of that is that you can fit pretty good single tree models. And that's what I'm going to talk about first. So so in this recent paper, the idea is very simple. Just remove the constraint on the partition points. So now in a multidimensional setting, you can randomly choose a direction to cut, the D, and then you can also randomly choose a location to cut. So you embed that hyperprior into your as a layer in your model. So this is the layer, the hyperprior on the tree. I'm using a curly tree. Introduced using some hyperparameters that characterizes the direction and the location. Right. It turns out that this eta parameter is a Laplace parameter that characterizes a Laplace prior on the cutting location. Because if you make the cutting location too flexible, you can also introduce another layer of variance that's due to overfitting in the cutting location, and introducing this Laplace prior essentially incorporates L1 penalty on the deviation away from the middle point. We found that to be very effective. And in the paper, we have some theory that justifies that choice as well. But I'm not going to get into detail in this talk. Now, in the general form, given the tree structure, we may have a downstream model that could have latent states, which may have a Markov structure. And then given the latent states, have our conditional prior on the splitting probabilities, which this general model encompasses all of the examples pretty much we saw in the context of Polya tree and their extensions so far, right? So let's, so what about the computation? So it turns out that there are some recent literature, especially this first paper, which is very useful. Oh, sorry, this is a typo, Lu and Wang. Oh, that's from Wing Wang's group, which these two papers in 2013 considered strategies of using sequential Monte Carlo to build as a computational strategy for sampling tree posteriors. And the idea then, so our first goal here is to adopt that strategy, right? We consider a sequential Monte Carlo strategy. We construct a sequence of target distributions where the curly TT is a finite tree that has to be terminated after splitting T times. So it's a T node, T plus 1 node tree, finite tree. And then pi T is the posterior on the space of these T plus 1 node trees. That's computed if you assume that your prior will terminate on any tree that the prior on the tree space is such that you will terminate the tree once it reaches T plus 1 node. So this is of course not the actual prior that we use, which does not terminate at level T, but you can use that to build a sequence of targets that approximates the eventual goal of the posterior tree posterior that we want to sample from. So the strategy is mostly following the standard Monte Carlo, sequential Monte Carlo strategy. For the target distribution, the prior is known by the essentially the variant of the card prior. And then the marginal likelihood is what we needed to update those importance weights sequentially. And I just want to point out that once you are given a finite tree, dyadic splitting tree with T different node, then the marginal likelihood is a standard marginal likelihood for the, let's say, a Polya tree on the finite given one-dimensional tree. So we know how to do that analytically. This is what people have been using for hypothesis testing for fixed tree, but now we can use that to compute this marginal likelihood, and based on that to update the weight in the sequential Monte Carlo. Now, this is just a cartoon, so you may have m different particles, which in the first step, you randomly propose a direction to cut, let's say, and the proposal that we built is based on one step. Okay, I'm not going to get into details on that, but let's say that this is the first proposal, and then for the next two blocks, you draw again another direction and location from the proposal distribution for this node, and then in the third step from this node. You always grow the tree breadth first, and then every time you split one node into two children, you can update the weight by utilizing your as long as you can know you can compute the marginal likelihood given the fixed the finite tree that you've generated. So using this strategy, we can pretty effectively sample trees on spaces up to 100 dimensions, and it's very fast. We can draw thousands of particles in a matter of minutes on a single desktop core. Okay, so this is just a plot on the scalability, computational scalability. One is the fixed dimension 5, and it scales linearly with sample size, and then also a fixed dimension, sample size 10,000. It scales pretty much linearly with dimensions. So let's just look at any numerical example. So let's say that in this very simple example where the underlying truth is this blocky density in a two-dimensional setting. In fact, what we did is, I think about in the paper is about a 50-dimensional example, but you can think of this as projections on the two-dimensional structure. So So if we have fixed partition that's always in the middle, this is kind of the map estimate that you can get from that, right? You see that there are a lot of unnecessary cutting along the boundaries, which is kind of the issue of the overly restrictive partition lines. Whereas this is what's coming from a flexible partitioning. And still, it's not perfect, but it's a lot more effective and is able to address the data attrition problem much more effectively. You avoided a lot of unnecessary cuts. Now, if where the truth is kind of smooth and symmetric, the directionality isn't too strong, it's still pretty, using the fixed partition, you still have a pretty, you still have these kind of bias issues caused by predetermined partition lines. Whereas if you relax that partition points, then the single trees can explore the distributions in a more effective way. Because even though the overall distribution is symmetric, in any local regions, there's going to be some asymmetry that can be explored. So I'm gonna, given the interest of time, I'm going to skip that because I've been motivating the problem using density estimation, but in fact, this issue is more broadly applicable. It's more broad than one sample problem. If you have hypothesis testing problems where you can, for example, you want to identify two sample differences by allowing the partition grid to be flexible, you can substantially improve your power if you're not in a situation where the actual difference happens to exactly lie symmetrically at those prefix partition points, in which case, of course, you will lose some power. But otherwise, even in hypothesis testing, you will be improving your sensitivity, improving your power quite substantially. So the last part of my talk is that now that we have a device to build very flexible tree-based unsupervised problems, how about ensembles? Because we know that the best you can do with a single tree model is still quite limited. And in our supervised problem, we saw that Bayesian CART cannot beat BART, right? BART is way better than Bayesian CART. But if we know how to build those single tree models, can we use it as base learners or weak learners so that we can build an additive, for example, additive ensemble, such as boosting or BART for unsupervised problem, right? So that's the final objective here. So in the regression problem in the supervised setting, the model on which boosting and BART is based upon is this additive regression model, where the observation is coming from some. Oh, sorry, this is a typo. Yeah, there should be well, I'm not going to fix it, but the error. This should also have an error term. But you have a additive. The mean has an additive structure coming from capital K piecewise constant functions. And then by enforcing each of these GK, the base learner to be weak in the sense that they cannot have too many blocks so that, and they cannot deviate away too much from zero, you can make sure that each weak learner has very low variance. But at the same time, by aggregating a huge number of them, you can also reduce the bias. So at the end of the day, you get low bias and low variance, right? So the boosting algorithm, the classical boosting algorithm, not the gradient boosting, is that you can iteratively fit the next weak learner given your previous fit by fitting, let's say, the next regression tree to the current residuals, which is the difference between the original data from the current fit, and iterate on that, right? The later gradient boosting is useful when your loss function does not allow you to compute actual residuals, so you can use the gradients at the training data as so-called pseudo residuals. I'm not going to talk about that. So what I'm after here is to come up with this unsupervised counterpart of this fitting strategy for a supervised additive model. But now the problem is unsupervised. So we think our target is some unknown sampling distribution from which your IID data is coming from. And then you want to represent them as additive addition of k single tree models. Like each of these could be one of the single tree Polya tree based multivariate Polya tree based model, as we saw earlier. Okay, sorry, let me not mix the two together because the Polya tree is actually a prior on each of these. The model itself is just like a piecewise constant density that's built upon a recursive partition tree. So let's not bring in the Polya tree part because it's a prior on that. Those are separate issues. I'm talking about the sampling model. So the goal is to formulate these additions. There are two questions to address. So what should be the appropriate addition? And if we want to compute, come up with a fitting algorithm that's analogous to the supervised problem, we also need a notion of residuals, which corresponds to removing the current fitted measure from the set of observed data to get a set of current residuals so that you can fit the next base learner to it, right? So the envisioning of the algorithm would be that formulate some appropriate loss function, as we'll see. I'm not going to explain why, but it turns out that the appropriate loss function is the cross entropy loss, or in other words, the log likelihood. And then you iteratively fit the next base learner. And then after you fit the current step, you subtract. I haven't talked about what this subtraction is. You subtract the current fit from the current residual to get the next set of residuals in the case step and iterate. And that will fit the, that will be a boosting algorithm for the additive model. I did not talk about BART here because I will see, I'll briefly talk about why fitting kind of a BART type Bayesian model is a lot harder here than the boosting algorithm. If I forget, you can ask me at the end. So the idea is now we need to formulate notions of addition and subtraction or residualization in the sense of subtracting a measure from a data point to get a data point from some distribution that from some other distribution, right? So one observation is that if you think about a data point coming from a sampling model, sampling distribution G, let's, for simplicity, start off with the Wendy case. I know that I'm out of time. I'll finish in 5 minutes, and to leave some time for questions. So if X is from G, and if we use both G to represent the CDF of G, then let's say for simplicity, let's imagine that the G is continuous. Then we know by basic probability that the CDF transform, after applying the CDF transform, you get back the uniform distribution. Let's say that the support is 0, 1. In other words, this CDF transform seems to be doing the trick of removing the structure of a measure from a data set, right? So if you have IID data from G, then applying the CDF to all of them, you get an IID data set from uniform 0, 1. So it seems to be that the uniform distribution is a natural 0 in the collection of probability measures, and the CDF transform corresponds to taking the residuals, right? So then we can come up with a corresponding addition that's consistent with the notion of subtraction that we just talked about. So what do I mean by consistent? Consistent meaning that if X is distributed as a distribution, which is the sum of G plus H, then if we subtract G from X, like we did on the previous slide, then the residual should be distributed as H. So if this addition satisfies this star property, then we say that it's consistent with the subtraction defined by CDF transform. It turns out that the appropriate addition is very simple. The addition of G and H corresponds to taking the CDF composition. So if we take the composition of H and G to get a new probability measure, CDF, then this F will be the probability distribution from which X is distributed, such that if you take the residual from G, it will be distributed as H. So that gives us a very simple solution, at least for the Wendy case, that we can have a boosting algorithm, for a stage-wise fitting boosting algorithm, by iteratively maximizing fitting the base learner, tree learner, by maximizing the log likelihood of the current residual, right? And you can replace this step. You don't have to do the maximization step. You can replace this using, for example, the Polya tree model that I talked about, which essentially you can show that is approximately solving this optimization problem if you take, for example, the posterior mode. And and then iteratively update your current fit and then get the next round of residuals, which is just applying the next CDF transform to the current residual. And then you can update the fitted density at the training data points by, it turns out that the fitted density is exactly additive on the log scale. So you just add the current fitted density to the current residual to the existing fit for that data point, you will get the current fitted density. So there's no integration or differentiation involved, even though you are able to fit both the CDF and the density. You don't have to take differentiation. So it's very simple. So now in the multivariate case, life is a little harder because the traditional notion of CDF on multivariate spaces does not allow you to take compositions because it maps a d-dimensional vector to the unit interval, and you cannot compose that. The fundamental reason for that you can show is that the CDF, 1D CDFs, they form a group, and somehow the classical notion of multivariate CDFs does not form such a group. And the group has identity, which is the uniform distribution, and this addition and subtraction corresponds to the composition of the corresponding CDFs. So in the 1D case. So now let me touch upon why BART fitting or backfitting algorithms is a lot harder than here, because the backfitting algorithms, including the way you fit BART, is requiring the group to be a abelian group. But in the Euclidean space, the usual group structure is in the supervised setting is abelian, but here the group structure in the unsupervised problem is not abelian. So it's a group, but it's not an abelian group. It's not commutative. So that's why in this paper we adopted the boosting algorithm, not BART. Right. So the objective is to formulate a group structure where we need to have a new notion of multivariate CDF that maps from the d-dimensional space to the d-dimensional space. It has the zero, which is the multivariate uniform, and then we'll also have this corresponding star property if you define addition based on the composition of the new notion of multivariate CDF. I'm going to skip the details, but the short story is that although the problem at first sight seems not obvious, trees again save the day. It turns out that the univariate CDFs can be actually also represented in terms of a multi-scale tree decomposition, also in terms of a sequence of compositions of local binomial Bernoulli CDF compositions. What does that imply is that in the multivariate setting, once I am given a partition tree, if you give me a partition tree, then again, think about the partition tree essentially reduces the dimensionality of the data down to one-dimensional. So you can actually basically apply your sequence of compositions at each tree split according to the direction of that tree split to move to transform the data as if it's a one-dimensional density that's whose gradient is only in that direction. It turns out that you can indeed prove that you can come up with a similar notion of multivariate CDF that's generalizing this idea of one-dimensional CDF, which has all the group structures that we wanted. So it turns out that after we posted our archive later, it was brought to our attention that there's a similar idea has shown up just 1 year before we started thinking about this problem. In this not that well-known paper, so we were not aware of it, but it's a very nice paper. You can read it. It's called Tree Density Destructors by these authors in the machine learning literature when they think about transforms of normalizing flows, which I'm not gonna, there's a deeper connection, but I don't have the time to talk about it. I'm gonna skip that, but I'm just gonna stop with the last numerical example. If we go back to the true densities of these types, right? And you can introduce, again, analogous to supervised problems, there's so-called learning rates, which basically is a shrinkage toward the uniform so that each tree-based learner is only deviating away from the uniform a little bit. And then you generally need a pretty small weak learners, especially for smooth densities. If it's very blocky, then you can a high learning rate is actually better, right? So, and if you look at the fitted density, I don't know how good your screen resolution is here, but the top row is a low learning rate, so you fit a lot of trees, hundreds of trees, and then this is the bottom row is a high learning rate, so it's closer to single tree. As you can see that for those smooth densities, the single tree learners or the high learning rate learners are very pixelated, very blocky, right? As you would imagine. But if you impose weak learners, a lot of trees, then it smooths out the issues of single trees. Now, of course, if the truth is very blocky, then that doesn't really buy you much. All right, I'm going to stop here. And to summarize 3 points, I think trees do matter and they are helpful. And if you've been using state breaking processes, you are using them without noticing, perhaps. And a second comment is that good trees can be learned. And even in high dimensional settings with recent computational advances. And then finally, even in unsupervised settings, trees can and should be added if your goal is to estimate probability measures in high dimensional settings. Thank you all for your attention. That's all of my presentation. Yeah.
So thanks, Lee. Good talk. So are there any questions for Lee? Ed, see it there.
Hi, Lee.
Hi,
Always wonderful to hear your talks. And this is so interesting at the end to try and do an unsupervised BART here. And so one question a little bit is, in the supervised setting, right, you can subtract off all the trees and now you have a single Bayesian cart problem. But is it the case that here I didn't quite understand the subtraction. I guess it's something to do with applying the CDF transform to get you close.
It's exactly the same. So in the sense that in both BART and for stage-wise fitting, in each step, what you're tasked with is fitting a single tree-based learner, right? Okay. So what BART is doing is that it does not loop through the trees only once. It's using backfitting. Every time you subtract all the other trees, get a new set of residuals, and then fit the next tree, sample the next tree corresponding to that set of residuals, and so on and so on. And you loop through the trees again and again. What I'm doing here is just the boosting algorithm, which is fitting this trees in a given order as opposed to looping through them. The reason is that I briefly mentioned that because the notion of addition here is not the addition here is not commutative. So in order to in order to be able to subtract trees from the fits in any order, you need the addition and the subtraction to be commutative. It turns out that because this is not available here, BART is difficult. We worked with some approximation strategy to fit BART, but the improvement in the performance is minimal, so we did not end up doing that.
So actually, my second question was going to be that it seemed that in boosting, what you do is you keep going forever, and then you just reweight, and that's the idea. And you just stop, I guess, when you're getting close enough to a uniform in residual. Is that right?
Yeah. So I did not show those. So these are if you plot the KL. So here we know the truth, but you can actually plot if you have a testing set of some kind. You can actually see that the performance will decay if you have too many trees, and then it will stop when you choose the number of trees in a sweet spot where the performance do not decay much. Yeah.
Great. Thank you. Good.
Oh, thank you.
I have more questions, but I'll let other people ask first.
Yeah, feel free to reach me. I'm sure I will meet you in person at some point. Pretty soon.
Great.
So are there any more questions for Lee? So I had a question. So you have this compositional idea. So is there, so potentially you can then have very weak learners and kind of compose lots of very weak learners. So is there some way of understanding how weak the learners can be, or that trade-off?
So how weak the learners can be. In general, in our examples, we've used many very, very weak learners. So so basically for each distribution, just like in supervised boosting or BART, we've used hundreds of trees. And we found that to be doing best. And generally speaking, when you have hundreds of trees, the point at which the performance start to decay is actually the range of number of trees is actually very wide. So you won't have to worry too much about overfitting by including the tree until you have like really too many trees. So we generally would recommend a large number of trees, hundreds of trees. So each only removes the structure in the distribution by a tiny little bit. Move it toward uniformity only a little bit, right? So I did not talk about shrinkage, but it turns out that the lessons that we learned from Polya tree literature is helpful here. In general, in the supervised boosting literature, people have a universal global shrinkage learning rate that, a constant C for the entire fitted function. It turns out that this is learning from Polya tree because different parts of the space may have different smoothness, and the shrinkage may be, you can actually come up with a level or no specific shrinkage so that you can actually adapt to different parts of the distribution at different rate. And I think this lesson is probably useful for supervised boosting as well. It's just never explored. Yeah.
Great. You read my mind. I was going to ask about shrinkage.
Yeah.
He read my mind. So that's so I have another question. On your earlier part of your talk, you were talking about the adaptive Polya tree, but it seemed, I mean, what about using these like balance splits and stuff like that? I guess you do that in a cart tree. So, I mean, I was just wondering if there's a way to enhance the sort of tree process for BART and use these enhanced trees in BART. Have you ever tried that?
We haven't enhanced the tree single tree part very much. I think there's very much room for future improvement and there are many techniques that can be tried to enhance on a given model. We did not explore those strategies very much.
I love the sort of the balanced splitting. Seems so much smarter to me. It always bothered me that you go down one side.
No, you're too humble.
It's a great idea.
So I had a question about balance splitting actually. So how does it mix if you run MCMC on that? So in a way, in stick breaking, right, you have this problem of the ordering, right? So here it seems like that problem is almost magnified because you can kind of, it can be over here in the tree and maybe you want to move it over there in the tree. And in theory, at least in your MCMC, you should kind of mix over all these very kind of different configurations.
Yeah. So first of all, maybe this was not clear in the talk. So this is an interesting comment, which I'm looking forward to working on that, which is that, for example, in the stick breaking setting where if you have a balanced tree structure, you no longer have stochastic ordering, but we're not learning the tree structure. We're not putting a prior on the tree structure and how fit MCMC to do that. So the MCMC sampling is just on the splitting probabilities and the covariate effect, if you have them. So so Akira is here. He knows a lot more than I do because he's fitted all those MCMCs. But some of the common phenomenon that we found is that if you have a lopsided tree like that, then you will have a lot more opportunities for label switching because think about it, if so you will switch those two labels very easily because you only need to modify one coefficient or something. And whereas in the balanced tree structure, it's not very easy to label switch. So depending on how you think of label switching, if you think of it as a benefit of mixing, or you think of it as a nuisance where you try to post hoc correct all those label switching, this could be more or less desirable, right? So because if you have a massive number of label switches, it's very difficult to keep track of how you correct them,
Yeah. Okay. Yeah, that's interesting. So you kind of get stuck in you have many local modes, but you tend to get stuck in one and you don't ever move out of it. Okay.
Yeah. The hope
is that a kind of very rough idea of
that's true, but at the same time, I want to mention that hopefully this prior, because this prior is fully symmetric, hopefully the local mode that you're stuck in is pretty representative of the whole posterior. Yeah. than this one, which
Right.
is highly asymmetric.
Yeah.
Thank you for the question.
About
That's a
that.
good question.
So there are other questions, comments? Okay, so thanks, Lee. I think I'll bring things to a close. So thanks for a stimulating talk.
Yes,
Yeah,
Lee,
thank you.
thanks. It was
Yeah,
wonderful.
thank you all very
Thank
much.
you, Jim, for doing this. You do such
okay.
a great job.
So
Absolutely.
we'll be back at the start of April for another talk. See you later.
See
Bye,
you.
everybody.
Bye.
Be well. Bye, Sonia.
Take care.
Ciao, ciao. Thank you. Thank you. Great
Bye-bye.
talk.
Oh, thank you.